Alright, so here are the objectives for today's class. First, I want to explain a little bit more detail about this week's homework assignment. It's a little bit more difficult than the homework assignments in the past, but it's also a lot more interesting. And then we'll review nested loops, and we will understand the difference between the break and the continue statements when they are in loops, and then quickly discuss the use of enumerations. Alright, so first I want to talk a little bit about this week's homework. This week's homework is going to be a little more difficult, so please don't put it off to the last minute, but it's also a lot more interesting. And it deals with encryption. So here's just a definition of an encryption, which is the process of converting ordinary information, which is called plain text, into unintelligible text, which is called ciphertext. And the challenge with encryption is that you want the spy, someone that is listening to your communication, not to be able to guess the plain text without substantial brute force work. But you want the recipient to be able to do it, read what you mean with very little work. Any encryption is going to be susceptible to brute force. You can always just try every single possible combination. But usually, if your encryption is good, it requires so much work that a spy wouldn't be able to do that in a reasonable amount of time. The type of cipher you're going to be writing in this week's homework is called a block cipher. What that means is you're converting n plain text bits into n ciphertext bits. So the size of the input and the output are the same. Some encryption works with changing the size of it, and like a hash function, for example, converts things of variable sizes into something of the same size. But we'll be doing a block cipher in this case. And here's just kind of a picture representation of what we want to be able to do. We want, Bob over here to be able to talk to Amy over here, and we want them to be able to discuss things fairly quickly. But if this spy is listening to what they're saying, the spy doesn't understand what they are discussing. So they're going to be sending encrypted messages back and forth, and they need to be able to decrypt it fairly quickly so that they can communicate more or less in real time, whereas the spy would take a very, very long time to understand it. And this is like pulling encrypted files off of a web server or off of cloud storage. You want to be able to encrypt and decrypt very, very quickly. All right, so the particular cipher that we're going to be doing this week is called a Feistel cipher. It's named after the inventor of it, which was last name was Feistel. And here's a diagram on the right-hand side taken from Wikipedia, which shows the encryption scheme and the decryption scheme. You're only going to be writing the encryption scheme in this week's homework. So I'm going to explain all these blocks here in a little bit more details in the next few slides. But first I'm going to just define what is called a pseudo-random function. And we've looked at pseudo-random functions before. In fact, the rand function that we have called before is a pseudo-random function. So more generally, a pseudo-random function takes some set of information, and now we can think of it in terms of cryptology, some plain text, and then converts it into something that's ciphertext that you would never be able to guess the location. And so you can imagine if your plain text was A, B, C, D, E, which have some sort of regularity as we're moving through, it would be encrypting it into just random locations, so that if you were to look at some particular location here, you would have no idea where it came from. So that's what a pseudo-random function does, is it takes an input and outputs something that you would never be able to kind of think about it in the reverse direction. So the particular pseudo-random function we're doing is a linear congruential generator. And we've looked at this before in a few classes ago. And an LCG, linear congruential generator, can be a pseudo-random function. And I'll explain what some of the requirements are for that. But it's actually used in many standard libraries. In fact, glibc, which is what we tend to use with our compiler, uses it. Visual Basic, among many others. So this is a very common pseudo-random function. It's actually fairly simple to implement. And so we've seen this before. Simply, we take an input, which is x sub n, and you can think of that as your seed value, your first value, multiply it by a constant, add a different constant, take the modulus of yet a third constant, and then it's going to get an output. And there's the output of your pseudo-random function. And so looking at this output, you would never be able to guess what the input is. That's the idea of it is actually truly pseudo-random. Pseudo-random because this is a definitive function, and so anytime I put in a particular value of x n, I'm always going to get x to the n plus 1 out. So it's not truly random, it's called pseudo-random. So here's kind of a quick, just kind of a picture of how this would work. So here we've got some constants, m, a, and c. And we've put some fairly simple values here. In practice, these tend to be much larger values. So if our input, we start off with a seed of 0, which means we're going to put 0 in here for x to the n. We multiply it by a, that's still going to be 0. Add 1 to it, so now we've got a value 1. 1 modded by 9 is going to give us 1. So the next output is going to be 1. So we start at 0, we get a 1. And we put 1 in here, multiply by 4. So we're going to get 4. Add 1 to it, we have 5. We have 5 mod n. Well, that's going to give us 5. So our next output is going to be 5. And we keep going. 5 times 4 is 20, plus 1 is 21. Now we have 21 mod 9. So 21 mod 9. And that right there is going to be equal to 3. And so our next output is 3. And what this does, you can kind of think of it like a clock. It just kind of keeps going around. But where it lands is sort of random. And that's the idea behind it. So it goes 0, 1, 5, 3. It doesn't seem like there's any particular pattern to it. Here's some output that I just generated using Excel, and I used some different constants. Again, pretty small constants, but they kind of help. It's easier to see what's going on. So I have the values of A is 17, C is 23, M is 43, and this is just the first 41 values. And what you see is it looks fairly random. You have no idea or any particular value what the next one would be or what the previous one was. And if I change the value just subtly, so I go from 23 to 29, not a big change. I keep the other constants the same. We have a very different looking function. So this is clearly very difficult in order to predict what your next value would be or what the preceding value was. This is what's called a trapdoor function. The idea that it's very easy to go in one direction, but very difficult to go in the opposite. And what that means is, right, if I have this value and I stick it in there, I can easily get the next value. I just put it into the linear congruential generator, which is that function there. But given what this value is, I can't go back. So I can't give an x to the n plus 1. I can't predict what x to the n was. So it's called a trapdoor function. Easy to go one way, difficult to go the other way. All right, so back to our Feistel cipher and what we're doing. And our trapdoor function is this function f right here. That's the linear congruential generator, the LCG. Right? And so this is what you're going to do. You're going to take some plain text, and you're going to break it into characters. And you're going to take each individual character, and I'm going to put, say, a T there and an E there. That's what the L and the R is. So you're going to operate on 2 characters at a time. And you're going to put them in there. And then you're going to typecast these that are characters as integer values. And so, for example, my value T, which is a decimal value of 116, would have this binary representation. And then that's what's going to be put into these functions. Now, first you take one of these values, the value of E in this case, and put it into your LCG, and then you're going to get a different value out. And then you're going to go ahead and XOR them. So first you use the LCG as a trapdoor function. The value K, right over here, the key value is the number of iterations that you do in the LCG. So remember, you have x to the n, n plus 1, n plus 2, n plus 3. And so K0 is going to be how many you're adding to n. So you're going to kind of loop through that LCG that many times before you output it into this point. Then you're going to go ahead and XOR those two. We saw a bitwise XOR in the last class. And you're going to XOR those two right there. And then you're going to go ahead and do another one. So here's another round. This is called, each one is called a cipher round, or a Feistel round 1, 2. And you're actually going to do it 3 times. And then once you're done, you're going to go ahead and output these values down here, which is your cipher text. And what these are going to do, you're going to output them as hexadecimal values. And we talked about those in last class. And the reason is you won't always have a char value, a principal char value that comes out. Remember, there's other ASCII representations, things like new lines and carriage returns that you can't really print to the screen. So we'll always print them out as hexadecimal. All right, so let's do a quick example just to kind of see exactly how the Feistel round works. So here, my 2 inputs are S and H, are the first 2 letters that I'm working on in my string. And so here's the binary representation, and this start over here is the left-hand side. This is the right-hand side. And I'm going to go ahead and put it in. So I take this value of the H, I run it through my LCG, and say I get, depending on whatever my key value was that I put in, I have this binary number here. Then I XOR that one and this one, and that's going to give me the new output. So that's at this point right here. And then I go ahead and just swap them. And I'm going to do it 3 times. So the homework specifies that we do our 3 Feistel rounds, and then we're going to output our cipher text. The value key naught, the user inputs. And so you'll see in the example, the user inputs the text, the plain text, and the value of k. And then each one, k1, is going to be just simply k naught plus 1. K to the n is just going to be 1 plus k to the n minus 1. So you just add 1 to the key value every time. We start out with key value of 12. This one would be 13. The next one would be 14. So it's fairly simple. In reality, keys are done a little differently, but we won't worry about that detail in this homework assignment. All right, so just kind of a little bit of hints, and the Zybook mentioned this in terms of incremental programming. Don't try to write this whole encryption scheme in one go. you probably will have a mistake somewhere, and it's hard to find out where it is. So I'd recommend is to kind of take it piecewise. Now, first of all, you're going to have 3 nested loops. So let's look at it. First of all, you're going to be looping over all the characters in your text. So, for example, if I just had simply a 4-character text, T-E-X-T, I would do T and E, and then I would do X and T. So you can operate 2 at a time, and go on. And if you happen to have an odd number, you're just going to add a space to the end. That's specified in the homework assignment. Then, in each one of these 2 characters, you're going to loop over the Feistel rounds. We have 1, 2, 3. Homework specifies to use 3 Feistel rounds. And then, in each Feistel round, you're going to be looping over the number of iterations of the LCG. Because remember, X to the n plus 1 is A, X to the n plus C mod M, and that would be once, and then if I do it again and make this n plus 1 and that n plus 2, that would be the second time. So you're going to each time do it k values, and that key member changes each time. It just becomes 1 more than the last one. So there's a couple things that can help you do when you're doing this. I would recommend first write your LCG, so that's the innermost loop, and if you test it with k equals 1, it's pretty simple because you can just go and analytically stick it into that equation there and make sure that your LCG is working correctly. Then go ahead and integrate a single Feistel round, so then put a loop on the outside of it. And if you test that with a key value of 0, this input is going to be the same as the output. And then all you need to do is check your XOR operator and make sure that that's operating correctly and that you're swapping of those 2 values. And then you can go ahead and loop through all the characters. So just sort of take it incrementally. It's just kind of a little advice on making this programming assignment not too difficult. Just so you know, this is only about 12 or 15 lines of code, so although it sounds fairly complicated, when you actually write it, it doesn't take too much. Each one of these steps is about 1 line of code. All right, so let's talk about some of the other topics that we looked at in the reading this week. First, we're going to talk about nested loops. Loops inside another loop is called nesting, and because computers are fast, we tend to loop a lot of these so we can operate on things in multiple dimensions. So that's when they tend to be used. And so usually you use the for loop because usually you know what your dimension size is. Very rare that you would end up using a while loop in a nested loop just because of the fact that if you're trying to go through multiple dimensions, you probably know what those dimensions are as ahead of time as you're operating in there. Here I just give a quick example of a nested loop where I'm computing a value at every latitude and longitude on the planet. So my latitude is going from -90 to 90, so I'm going to have 180 latitude values, and then at each latitude I'm evaluating at all of my longitude, so I have 360 longitude values. And each time I'm just going to output, imagining I have some function called get elevation that finds the elevation at that point. And so the number of iterations for this is going to be 180 times 360, because it's going to go through this inner loop 360 times, and then it's going to go outside and increment that 1. So you're going to end up with a lot of values there that this ends up doing. So you realize nested loops can generate lots and lots of computations, so it's a good thing computers are fast. All right. Sometimes the ordering of the nesting matters. And so, for example, if you were to say you wanted to print permutations in alphabetical order, so I'm just going to go through letter A through D, and then A through D. So I'm printing 2-letter permutations. I'm starting off with AA, but I want to print AB. I don't want to print BA because I want them to be in alphabetical order as I move through. So I want to make sure that as I'm iterating, my inner loop is the second character that I'm doing as I move through. So if I wrote it this way, they would be truly in alphabetical order: AA, AB, AC, BA, BB, BC. If I was to switch those and make this one first and that one second, it wouldn't end up being in alphabetical order. So although I would go through all the permutations, I wouldn't have something in alphabetical order. So sometimes the ordering matters, so be careful about that. All right, so here's the first quiz question. It's just evaluate how many times this loop is going to occur. So how many times is this line of code going to be executed where it's going to write val? And I have a nested loop here where I have I going from 2 to 5 and j going from 10 down to 0. Okay, well, the answer is it's going to do 30 times. And what we can see is that each time j goes from 10 to 0, well, it has to be greater than 0, so it's actually going to go from 10 to 1, which is 10 iterations. And then it does it 3 times because it does it as I is a value of 2, 3, and 4, and then it will no longer be 5. So that's going to be 3 times. So 10 times 3 is 30, so it's going to be 30 iterations. All right, let's look at the break statement. This is a way to exit a loop early. And sometimes you want to leave a loop early. And an example of this would be, say, an error occurred in some iteration, which means that you got to get that fixed, and there's no reason to go through all the other iterations of the loop because there was some error that occurred. And here I kind of give an example back to my latitude, longitude, where I'm getting the elevation at each point. And then here what I'm doing, I'm testing. Let me explain this a little bit. I'm finding out if actually it returned a value that's not a number. And so I'm saying if elevation is not equal to elevation, and that seems sort of like that could never actually happen, and then I'm breaking out of the statement. It turns out it can. There's something called NaN, which is not a number, and you run into this often in different computer code. And this is a reserved binary number that says the computer, this doesn't actually represent one of the numbers in there. So think back to binary, right? We had 000, 001, 010, 011, etc. And then we had like a choose complement where each one of these would correspond to, say, 0, 1, 2, and then like -4, -3, -2. Well, there's an IEEE standard for this, and often one of these values, and the particular one doesn't matter, is reserved to not represent actually a value, but it represents not a number. And so if this binary number is evaluated, or is output from something, it means there was an error in the code, it wasn't actually computing a number, and this right over here will evaluate to true. And another way to do that is there's a function called isNaN. It's included in the CMAP library, and if you do that, this will evaluate the true if elevation doesn't equal a number. So if you divide by 0, for example, that often gives you not a number. Alright, so here's the next one, and now we're introduced the break statement. So we want to know how many times will val be printed, how many times will this line of code happen. And one of the things to remember, so break means it ends this loop, it ends the inner loop, and it's going to go back out to the outer loop. Right. Well, the answer is it's going to do it 21 times. Now, when does it break? Well, when j gets less than or equal to I. Now note, j starts at 10 and goes down. I starts at 2 and goes up. And at some point when they're equal, it actually stops and goes to the next iteration of I. And so we realize that the first time j is going to start at 10, and it's going to go down to 9, 8, 7 until it becomes 3, and then I starts at 2. And so then the next iteration, when j is equal to 2 and I is equal to 2, it's going to break, which means it's never going to get to this statement. It goes back out to here, it increments I from 2 to 3, and it goes again. So it's going to do it 8 times the first time. But now I is a little bit larger, so now it's only going to go, j is only going to go 10 to 4. It's going to be 7 outputs, and then the next time 10 to 5 is going to give me 6, and if I add up those 3 numbers, it's 21. So this is actually going to execute this line of code 21 times. Let's look at the continue statement. It's a little bit different. It also leaves a loop early, but what it does is it sort of skips a step of the loop instead of ending the loop completely. And so it just skips the next iteration of the loop. And an example of this would be, for example, if no further processing is required just for this particular iteration. We don't want to end the loop, we just want to skip this. So imagine, here's my example, I'm iterating through the number of students that I have. Now, as I'm going through, maybe I'm computing their grades. But some of those students in the roster will be not enrolled. So imagine there's this function that says .enrolled. It determines whether the student is enrolled or not. So if they're not enrolled, it would evaluate the false. This is an array notation we'll talk about a little bit later, but I'm looking at this particular student corresponding to index I. Now I don't want to evaluate all this other stuff, so imagine I have other lines of code below it, but I don't want to quit processing students. I'm going to want to go to the next student. I use continue. It just says, oh, and go to the next iteration. Don't end the loop, just go to the next iteration of it. So it's slightly different, and the key is it skips that particular record. So here's the next kind of quiz question. How many times will this val be printed again, that line of code there? Now notice I have a little bit different. Right at this part over here, I say if j mod 2 is equivalent to 0, continue. So evaluate how many times would this line of code happen. Okay. Well, the answer is it would go 15 times. And if you look, what this says is that j mod 2 is 0, continue, which says on all the times that j is even, skip that record. So when j goes from 10 down to 1, but you're never going to evaluate it at all the even times. So effectively, we're only going to do it when j is 9, 7, 5, 3, and 1. That's going to be 5 times, and it's going to do that each time for I. There's no changes in I, so 3 times. So 3 times 5 is 15. So let's evaluate that to 15. All right, the last thing we'll do is discuss the enum data type. Enumerations are convenient data types, and they're used when there's some small set of discrete values are being used. And some examples of this would be, for example, if I had a finite state machine that had on, off, and standby. So a Boolean wouldn't work because I have actually 3 different values that I could have. Another one would be days of the week, where I have 7 discrete values. And the reason we use this is it just makes our code a little easier to understand. Underneath, it's simply an integer value. It's taking on discrete values 1, 2, 3, and 4. But what I'm going to do is I'm going to name those, give them particular names that are easy to understand. And it's best to see this with an example. So here's what I do. There's 2 steps to using an enumeration. First, I define effectively a new data type. It's like defining an int or defining a float. And then I define variables of that data type. So 2 steps. So first I type enum, there's my keyword. And then I'm calling this data type day of week, curly bracket. And then right here, I'm going to go ahead and list all my discrete values. So here I've got 7 values. I'm choosing the names. I'm doing month, to, when, etc. for the days of the week, ended with a semicolon. And using all caps is just sort of convention. It's not required, but you'll see why that kind of helps clarify what's going on. Now that I've declared a new data type, then I'm going to go ahead and say, here's my data type. Here are my 2 variables. I've got 2 variables of type, this enumeration of day of week. So there's 7 discrete values in each one, holiday and 4th of July. Okay. So now if I look at my code, right, I'm saying if 4th of July is equivalent to Saturday, which means that, then the holiday would be Friday, right? So it's pretty clear, right? If 4th of July starts on Saturday, my holiday is going to be Friday. Else, if 4th of July is, actually that shouldn't be Saturday, that should be Sunday, is what I meant to write. Okay? If 4th of July is Sunday, then holiday would be Monday, right? Because if 4th of July falls on a Sunday, we tend to make Monday the holiday for a 3-day weekend. Else, the holiday is actually 4th of July, so maybe that's Wednesday. So I assign Wednesday, and then it's going to be the Wednesday there. Okay. Now, the reason this is sort of convenient is because it's very clear what's going on. Right? I'm saying, well, if the 4th of July is this particular valid day, what is my holiday? Now, if I had numbers in there like 4th of July is 3, holidays equal to 4, you wouldn't know it's 3 and 4 is that Monday, Tuesday, and you'd always have to be going back to some reference. This makes it very clear to see what you're writing. So it's just a convenience. It's not required, but it's often used to make your code more readable. All right, well, that's it for today. Next class, next week, we're going to be looking at arrays, and I'll see you then.